Alright guys, so this is our second video for this week, covering another problem worthy of special attention from the syllabus. This is problem number 38 from section 4.4. So problem number 38 asks you to do the following. You're taking the integral from 0 to 1 of 1 plus x squared cubed dx. So I'd really encourage you guys to actually try to do this problem on your own for a minute and to pause the video before actually watching the entire solution. So take a second, pause, try it out, and then when you get stuck or maybe when you get it correct, press play again and we can go through the answer together. Okay, so without further ado, assuming you've paused and tried it, let's move on. So for this one, what I want to do is I actually want to expand what's in here so that I have a sequence of terms that I can take the integral over. I don't have good rules like the chain rule or like the product rule that I can use when I'm integrating. I really just have like a power rule and like those basic function integrations. So I've got to use what I've got, and so I have that I can add them together, so I'm going to use that. So yeah, without further ado, let's try expanding. So when I write 1 plus x squared cubed, what that actually means is that you're taking 1 plus x squared, and you're multiplying it to itself 3 times. So the way that we multiply is by doing some FOIL, doing some double distribution here. So I'm going to FOIL the first 2, right? And that'll give me the integral from 0 to 1, and I'm going to have 1 plus 2x squared plus x to the 4th. This is all times 1 plus x squared dx. Okay, so now moving from here, what I want to do is I want to distribute the 1 plus x squared. So multiply everything here by 1, multiply everything by x squared, and then add the result. So from that, you're going to get the following. You have the integral from 0 to 1. You're going to have 1 plus 2x squared plus x to the 4th. That's multiplying everything by 1, and now multiplying everything by x squared plus 2x to the 4 plus an x to the 6 dx. And of course, you can also use the binomial theorem here, but, you know, multiplying everything together doesn't require you to memorize a formula. So that's fair game made. Okay, so I've got the integral from 0 to 1. Now I'm just going to combine some like terms. I have 1 plus 3x squared plus 3x to the 4 plus x to the 6. So integrating, I'm sort of using the opposite of my power rule. So the integral, the antiderivative of 1 is x. Here, 3x squared. The x squared, when I integrate, becomes an x cubed. And then I need to divide by 3. So I would have 3x cubed over 3. So here, 3x to the 4th, 3x, and then 4 plus 1 gives me 5. And then whatever's up here, I've got to divide by that, so I divide by 5. And then x to the 6th is going to become an x to the 7th. And then whatever's up here, I divide. So x to the 7th divided by 7. So I'm going to evaluate at 1, evaluate at 0, and then subtract the result. So evaluating this at 1, I'm going to get 1 plus 1 plus 3/5 plus 1/7. Evaluating it at 0, since everything has an x term, it's just going to evaluate to 0. So my final result is going to be 2 plus 3/5 plus 7. All right, so we've just got to make a common denominator here. I'm going to multiply the top and bottom of this one by 7. That's going to give me 21 over 35. Multiplying the top and bottom of this one by 5, I'm going to get 5 over 35. Now I can just add the numerators and keep the common denominator. As a mixed number, this gives me 2 and 26/35. You could also write that as an improper fraction. Either way is fine. So again, just recapping what we did to try to solve this problem. Originally, we were given the integral of some binomial that has been cubed. I do not have a chain rule or a product rule or anything that I can use to attack that with. So what I have to do is I have to expand it so I get a long polynomial and I can take the antiderivative term by term. Once I've taken the antiderivative term by term, I put in the values for the endpoints and then I subtract. All right, so that's all for this problem. We'll have a couple more after this, so stay tuned. Thank you. Bye.